Hello everyone, welcome to Group 25 CDR presentation of our senior design project. Our project is called the Interactive Cat Toy. The members of Group 25 are two electrical engineering students, including myself, Vung Nguyen, and Elizabeth Vargas, and two computer engineering students, Joseph Lopez and Eliza Grabowski.
We are very thankful to have a sponsor working with us on our senior design project. Lei Fan is a mechanical engineer and author who is generously giving his time to take care of the mechanical design and the 3D printing of the chassis for our project.
It's estimated 373 million cats around the globe are kept as pets, with approximately 93.5 million pets here in the U.S. This provides for a large number of pet owners looking for toys to entertain their loving felines. Toys are a great way for owners to have fun and enjoy their time with their cats, while also giving them their needed exercise. But finding the right toy is the real challenge. Our senior design team decided to take this challenge and build the interactive cat toy.
Goals and objectives. With this project, we want to design an interactive cat toy that cats can be entertained by and engaged in play with for hours. We also want to incorporate elements into our toy that are key to domestic cat entertainment. Work to implement the current standards and the best safety factors that we can. Also, we want to design our ICT so that it can withstand rough cat plays and last for a reasonable amount of time.
We performed market and product research to help us plan the design for our interactive cat toy. This research helped us to identify key features that were proven to entertain cats. We planned to incorporate all of the key features that we identified into our interactive cat toy, but we also take our toy design further by adding control of select features to a phone application.
This table lists some of our project's requirement specifications. We have highlighted some requirements that are essential for optimal toy performance. The LEDs for our lighting effects need to shine bright enough to be clearly seen in a room with typical daytime brightness. Response from our motion detector should activate the device features within a reasonable time. And lastly, our phone application should not have excessive delay time. This is our hardware block diagram. Elizabeth Vargas is responsible for the battery charger, power supply, and the switch. Joseph Lopez is responsible for the mobile application and the Bluetooth module. Eliza Grabowski is responsible for the majority of the toy's component, which are LEDs, speaker, and motor. And I, Vung Nguyen, is responsible for the MCU with the PCB design and the motion sensor. For the toy, we have three hardware layers. The outermost layer is the interchangeable exterior skins. The middle layer is a protective chassis. And the innermost layer is electronics with the PCB and its components.
We decided to construct two interchangeable exterior skins for our interactive cat toy. The exterior skins are designed with the same measurements and a zippered opening so that the chassis can be easily switched between them. The chassis for our toy is designed to protect the electronics of the toy, to support toy features, and to be easily switched between the toy's interchangeable skins. The mechanical design and 3D printing of our chassis is being done by our wonderful sponsor, Lei Fan. Electronics for the interactive cat toy include our microcontroller and electronic feature components. All feature components for the interactive cat toy are RoHS compliant, ensuring environmentally safe products.
The main hardware components that we selected to build the interactive cat toys are listed in this table. Among microcontrollers, the RB2040 seems to be the best option for us to use with the interactive cat toy. For testing, we use Raspberry Pi Pico, which is the development board of RB2040. The specifications for RB2040, especially the amount of GPIO bins and the operating voltage, made it ideal for our projects.
For wireless communication, we decided to choose the M10 Bluetooth module because it is mainly compatible with iPhone and Android. It was a really good price. There are many options out there for Bluetooth, but the best recommendation is to use a module version 4 and above.
The speaker selected was Adafruit's Stemma speaker. It is small in size and has an amplifier built in.
We selected to go with the Tower Pro Micro Servo Motor from Adafruit to facilitate tail motion for our cat toy. Servo motors allow for embedded code to use PWM to control positioning of the gears, giving us just what we needed to correctly simulate tail motion. This micro servo motor is ideally sized and has robust metal gears, so it seemed perfect for the ICT.
The lighting selection was the NeoPixel Digital RGB LED strip from Adafruit. This is due to the WS2812 LEDs used.
Motion sensor selection. We decided to go for the PIR and mini PIR sensor. Comparing with other options, it was the one with the highest angle range.
Initially, we selected PETG to print our chassis, assuming its better flexibility would make it more robust for the ICT. When printing, though, the chassis was too rough and fibrous, so we switched to PLA. To determine our needed power supply, we added the approximate power usage for each of the toy's electronic components plus a 30% margin, as advised by Dr. Wade to cover leakage current and various voltage drops. We reasoned that the battery should power the ICT for about 8 hours on a full charge. This would allow enough time for entertaining cats during a typical workday. We compared nickel metal hydride and lithium-ion rechargeable batteries as a power source for our project and selected nickel metal hydride due to its lower volatility and cost. We selected a rechargeable battery because that is the standard for most electronic cat toys today. For our battery selection, we considered 7.2 to 3.6 volt battery packs with similar current ratings. We preferred to go with the 3.6 volt pack, however it was out of stock, and other 3.6 volt packs did not offer more than 1,000 milliamp hours. This would only guarantee powering the ICT for about 3 hours. For now, we decided to go with the 4.8 volt battery pack for our prototype. This pack is a good fit for the ICT with an acceptable weight at just under 100 grams. We employed TI's WebBench Power Designer to design a voltage regulation circuit to accommodate boosting power from either a 3.6 or a 4.8 volt battery pack in case a 3.6 volt pack should become available to us. We employ a switching regulator because of higher efficiency and the reduction in need for a heatsink. We boost the voltage to 5.2 volts, accounting for possible voltage loss over the circuit in order to properly supply enough voltage to power a 5 volt voltage bus. We considered designing and building a battery charger for our project. However, NIMH battery charging is significantly complex. Should we undertake designing and building a charging circuit for our battery, a considerable amount of time would be required. Building this circuit would almost be a senior design project in itself. And currently dealing with component supply issues, it would be even more difficult to compose such a circuit. Due to the complexity of designing and building an NIMH battery charger, we decided to use a prefabricated USB charger with built-in overcharge protection and an indicator light to alert when charging is complete. Our power supply circuit is designed to be switched between 3 positions. The first position allows for battery charging, the second position switches the ICT off, and the third position enables powering the toy through a voltage regulator. Switching for our power supply circuit is realizable with a double pole, double throw switch.
This is the schematic of our prototype. We have the battery regulator, USB and 3.3 volt regulator, an audio regulator, microcontroller, crystal oscillator, and the flash memory for the microcontroller. This is the layout of the PCB. The dimension of this layout is 3.25 inch in length and 2.5 inch in width. We follow the standard of IPC 2221A for our PCB design. And we also order the PCB prototype to be printed at JLC PCB. To test the components of the toy, we decided to use the Raspberry Pi Pico for breadboard testing. The Raspberry Pi Pico also used the same microcontroller as our prototype, hence making it easy for us to transfer our work onto the PCB. These are some of the standards that we apply in our hardware design of our interactive cat toy.
Software design. To make our project successful and fully functional, we need to use an application software and embedded software.
This software block diagram shows when the program begins, it starts by connecting to the Bluetooth device. It then checks to see if there's any input from the mobile application via the Bluetooth. If it does not get an input, it runs the base program's LED pattern, sound, and tail motion. If it does get an input, then it updates either the LED pattern, sound, or tail motion, depending on what was selected in the application. After running either the base program or updating program, it will check if the device is turned off or put on sleep. If the device is not off or on sleep, it will check the application input again. Otherwise, the program will end.
Application software. Our application is created in Android Studio. Creating apps for iPhone would force us to own a Mac, but with Android Studio, we could create apps in different operating systems, Windows, Mac, or even Linux. Also, there are more users around the world that use Android and not Mac. Based on the statistics from last year, Android is still leading the market with 70%. We are using Java is because there is a great amount of libraries and tools that could make it easier to create apps and be able to connect it with our toy and its features. Next will be the graphical user interface. This is how our application is going to look. The front page will have a clickable image where it will allow us to connect to the Bluetooth module. This part we're still working on it. After our app is connected to the toy, it's ready to use. It will send the user to a different page where we'll need to choose the features that wants to use. Could be changing the colors of the LEDs, send sounds through the toy, or move the tail in a different speed. Application capabilities. With our app, we want it to be user-friendly and easy to use. We believe that creating an app, the cats will have a better experience with its toy. Also, right now we are running the app on a simulator, but soon we are going to use a physical phone to be able to test the Bluetooth connection and be able to display the different Bluetooth available at the moment we try to connect. For application standard, these are the standards that will apply to our application development.
The lighting effects of the interactive cat toy will use the WS2812 LEDs. These provide a wide range of RGB color choices. The base model will have one color going down the LED strip, while the application will either have the choice of 3 colors going down the strip or a rainbow of colors going down the strip. To emit light on an RGB LED, it requires some current control. This is to avoid any LED burnout. To avoid burnout, we use a 50 ohm resistor between the MCU and the LED strip. Then, using the embedded software, we limit the lighting effects to use 60 milliamps. The code to the left shows the basic idea of how we will be programming the LEDs. The tail motion of our interactive cat toy will be utilizing a microservo motor to provide the tail wagging effect. The base model will simply move up and down at a steady speed, while the application will give the options of moving up and down halfway to up and down full way at a steady speed, or a quick movement of up and down. An added benefit is that we will add catnip to the tail, and the motion will set off a nice aroma of catnip in the air. The nanosecond method will provide a wide range of angles for the servo motor. In our code to the left, you can see 500,000 sets the angle to 0 degrees, while 1500,000 sets the angle to 90 degrees. The code then simply does a loop between the 2 degrees, creating a wagging motion. The stemma speaker of the interactive cat toy will be able to make many sounds that entice cats. The bass sound will simply be birds chirping on a loop, while the application can either be the sound of bugs flying or the sound of squirrels chattering. For CircuitPython to be able to emit sound from the speaker, we have to decode the MP3 file into a static array of numbers. After the MP3 file is decoded, we can play the sound through the speakers endlessly through an infinite while loop. The sensor of the interactive cat toy will establish the ability for sleep mode. This will allow the battery life to last even longer. With no interaction from a cat for a short while, the interactive cat toy will switch into sleep mode. When the cat triggers the sensor will send a message to the program to wake up and continue the base toy LED pattern, tail motion, and sound effects.
Our work distribution table represents how work for our project was shared among our group members. P distinguishes the primary and S the secondary members who are responsible for an area of work within our project. The cost to build our interactive cat toy came in at just under $200. Our project is being fully funded by our group members, having each student agreeing to pay 1/4 of the cost for the project. Our current progress to date has brought us to within approximately 60% completion of our senior design project. While we still have a lot of work to do to get our interactive cat toy fully operational, we believe that we have made good progress and will be able to finish on time.
Here are our challenges while designing the interactive cat toy. We need to consider battery size and its safety. Nickel metal hydride batteries are generally safer than lithium-ion batteries, as lithium-ion batteries can blow up if overcharged. However, it is also bigger and heavier. We also are having trouble fitting all components into the chassis. This problem will require us to spend more time designing the hardware layer. Moreover, the components are not working as intended, such as noisy audio from the speaker, and the PIR sensor is not too sensitive under the skin. Finally, many components are out of stock due to the pandemic, which forced us to find alternative solutions.
Throughout the initial pitch, our group made the effort to truly understanding a cat's likes and dislikes, while also taking into consideration the power consumption and the size of our cat toy. We kept the idea of having a relatively small frame, less than a foot, as well as having a mobile application feature. However, some of the changes that we made was from a laser to an LED, as a laser is larger in size, and from just a simple squirrel skin to an interchangeable skin. Though this is not hardware related, our team thought it was a fun touch.
Next steps. Test PCB connection with power supply, switching and components. Refine component fittings, chassis design and stereo skin patterns. Refine embedded programming for multiple feature expressions. Complete phone application GUI and ensure functioning control of toy feature through Bluetooth wireless communication. Ensure ICT meets requirements specification.
This concludes our presentation. We appreciate you taking your time to watch. Thank you.